Hello, I'm Eric. I'm very honored to be here today since this workshop addresses a topic which I think is really important to our community. I'm going to be talking about a particular perspective on lifelong or continual learning, focusing on factorized transfer. Before I get into that, I want to start by just taking a broad look at some of the topics that we as a community need to address. And these are topics that have been worked upon in various different manners, but for the large part, they still remain open issues. These are roughly organized from top to bottom in terms of how much effort we as a community have put towards these. So first off, we have things like long-term knowledge maintenance, avoiding catastrophic forgetting, and also learning from little data, things like zero-shot, few-shot, or general transfer learning. And these are topics that there's been a lot of work on, we've made a lot of progress toward. There's still ways to go, but it's a very solid foundation for what lies ahead. And that builds us to the second row. If we're going to take robots and deploy them for very long periods of time, we need not to be focusing on developing specific skills, but we want abilities that transfer across a large diversity of tasks. We want versatile robots. As part of this, we might also wish to focus on this idea of skill composition and reuse, possibly with hierarchies. How do we build up our knowledge from base level skills into solving increasingly higher level and broader problems? At the bottom row are topics which are important in lifelong learning, but there hasn't really been that much work on them, and I'll talk about them a little more in the end. Things like addressing non-stationarity and moving beyond the notion of tasks. And off to the right here, we have real-world applications. Specifically for this workshop, robotics and embodied agents, which I think is a really compelling application for work in lifelong and continual learning. I'm going to start by going back a few years, looking at a very foundational method which has been used for transfer learning, multitask learning, and also lifelong learning, and that's of the factorized task model. So imagine we're learning a model, ft, and it's parameterized by some vector theta t. If we could imagine doing this for a bunch of tasks, we would have collected a bunch of theta t's together, and we might factorize those into a common shared basis. And this basis is depicted off to the right here, where we have our vector theta t, some basis L over that model parameter space. And then in order to regenerate theta t, we would take different columns of L selected according to some set of coefficients. And if we share this basis across tasks, we can get a foundation for learning these theta t's. This has been used, as I mentioned, in a bunch of different methods. This is an objective function for multitask learning, specifically work by Kumar and Dame back from 2012 and Maurer in 2013, where what we have is an objective function over all the tasks. We take an average over those tasks. We have three terms. One's a model fit to data term using this shared basis L over the model parameter space. Then we also have a term for the sparsity of the coefficient vectors, as well as a Frobenius norm to regularize the complexity of the shared knowledge. For our early work in lifelong learning, we took this objective function and transformed it into a method that could learn tasks incrementally. We called it the Efficient Lifelong Learning Algorithm, or ELA. And this just takes this basic multitask learning objective, which uses factorized transfer, and transforms it into essentially an online dictionary learning problem with sparse coding. From this basic algorithm, which worked on classification and regression, my group developed a large number of other algorithms in the same family, looking at topics such as how do you actually select the tasks in order to maximize performance? Could we take this framework for classification and regression and then move it into reinforcement learning, specifically with policy gradients and also with safe policy transfer? We then looked at ways of learning this from demonstration, lifelong imitation learning. How do you do this when you have different state action spaces? Looking at cross-domain transfer in lifelong learning. Then we looked at topics including zero-shot lifelong learning from a task description to give us a jumpstart of performance. What happens if we didn't have just one agent, but we actually had multiple agents deployed in, say, different people's houses? Could we learn collectively knowledge over a lifetime of experience from all the agents? And finally, our more recent work in lifelong deep learning, which is where I'm going to be spending most of the time on today's talk. Now, our work on ELA is just one type of approach to lifelong or continual learning. And specifically, this is a multi-model shared knowledge approach, where what we have is for each task, we learn a different model, and those models are coupled together in some way, in this case via some shared knowledge base. Progressive neural nets are another type of this example of multi-model shared knowledge transfer for lifelong learning. Another approach, which many people take, is to have a single monolithic model for all tasks. And in this case, we really have a single model with integrated knowledge. So things like elastic weight consolidation, HAT, clear, progress and compress, all of this work uses just a single big neural net for learning all the different tasks. And there's a major focus on avoiding interference among the tasks. On another type of framework, we have things like HORD, which is by Sutton et al. It does lifelong learning, but there's no artificial notion of a task, and it just kind of seamlessly integrates perception and action streaming into the mechanism over time. And finally, we have structure learning frameworks, things like the never-ending language learner and lifelong topic modeling, which are very application-specific techniques. For example, populating an ontology and building it over a lifetime of experience. Now, to take these techniques and to move them into the problem that we're interested in, that of deploying lifelong learning on autonomous robots, we need a couple more things. So first off, we as a community are very good at taking a model which we've learned and then adapting it to a new task. So things like transfer learning or meta learning. But we're not really good yet at learning generalized and reusable knowledge, modular components that we can combine together, or skills that can be adapted and dynamically combined together to produce behavior on a new set of challenges. The second thing is that life really isn't broken into these artificial notions of tasks that we seem to address as a community. So for example, what task am I doing now? Am I giving a presentation? Am I talking? Am I standing? Am I balancing? Am I gesturing? There's all kinds of things I'm doing now that are dynamically combined together. And so instead of focusing on a lifetime of experience that's separated into tasks, we really should go for a much more organic notion, where there's simply a dynamic stream of sensory action perceptions and a dynamic set of goals that are being accomplished by the agent that may change at each point in time. And finally, how can we take these ideas for an embodied agent where we're perceiving and acting in the environment and integrate them together in a really seamless way for lifelong or continual learning? And so these are some of the topics which I'm going to start talking about how we've been trying to address in this talk. And I'm specifically going to talk about three things. The first is lifelong deep learning for perception. And then we're going to take and transition it into a more structured form of knowledge in terms of composable representations, looking at that both for perception as well as for reinforcement learning. And then I'm going to conclude with talking about applications to autonomous service robots. So first we'll touch on lifelong deep learning for perception. There are different ways of sharing knowledge in a deep net. So for example, a very classic way is you simply share representations. Hard parameter sharing does this, where we have some layers which are shared between all the tasks, and then you have a series of task-specific heads and possibly task-specific inputs coming in for different data modalities, for example. Another way uses tensor factorization, where the shared knowledge is more tightly coupled together, but it's still a little separate. And finally, we have things like progressive nets, which directly build upon the representations which have been learned previously. We're going to talk about a little different form of this. So this is our attempt to take the early work in factorized lifelong learning and move it into modern deep learning techniques. And what we have here is a networks for two tasks, task one up top and task two down the bottom. And we have a set of shared knowledge bases. Now, the shared knowledge bases are used to generate the filters for the corresponding layers. So in this case, for example, we have the two networks, which are both convnets with 4 different convolutional layers, followed by a series of fully connected layers at the top. And the convolutional layers that have filters that are shown in green don't actually exist for a single task. What we instead have is a set of parameters over the shared knowledge base that is then used to generate the filters for that particular layer using a series of deconvolutional mappings from the shared knowledge. And in this way, the networks for task 1 and task 2 are coupled together via the shared knowledge bases. We can also have layers which have filters that are task specific, and those are represented by the purely white layers in this diagram here. And our goal in lifelong learning is to train up the models for each task consecutively. So we train up task 1, where the gradients would flow through all the way back into the shared knowledge base. Then we would train up task 2, where the gradients would flow back into the shared knowledge base, and so forth and so on. We do not revisit earlier tasks. So, however, the model for those tasks may change as we adapt the shared knowledge base. So we ran a series of lifelong learning experiments, and what we see, we compare against, for example, multitask CNNs, progressive neural networks, dynamically expandable networks, and then we have ours too in the maroon and the red. These performance accuracies are all relative to single task learning accuracy, and what we can see is that the DFCNN has good peak accuracy in comparison to the other methods. We also show in the paper that it converges fast and has good knowledge retention capabilities. Here we show the dynamic behavior of the DFCNN in comparison to a standard multitask CNN during a lifelong learning experiment. As the algorithms first experience task 1 in red, followed by task 2 in red-orange, followed by task 3 in orange, what you can see on the left is that the multitask CNN clearly has interference among the tasks, and the performance drops off. So this is catastrophic forgetting. Whereas on the right-hand side, you can see that the DFCNN retains its performance over time. So it doesn't experience forgetting, or experiences very little forgetting, and it's able to continually build upon these the previous performance to achieve new levels of performance. Previous work has mainly focused on the architecture, in other words, what or how to transfer between different tasks, or the task relationships, in other words, when to transfer from one task to another. There's been a lot less work on where to transfer within it. So what we did was, instead of assuming that we should just transfer at all layers of the deep net, we asked the question about, well, what if we allowed the structure of the transfer to change depending on what the task actually needed? In order to motivate this work, we did a really simple experiment. What we did is we took the DFCNN and we took the multitask CNN over two different data sets, and we simply varied the architecture of which layers to transfer. If we look across the columns here, the optimal transfer configuration, the one that's best, just varies according to the architecture. In other words, whether we're working with a multitask CNN or a DFCNN. It also varies depending on what the relationships are among the different tasks. And so there's no best architecture to use to figure out what layers should transfer or not transfer. And so instead, what we did was we put this as part of the learning process itself. Now, there's a fairly large size of the search space because we have, for each layer, the question of, do we transfer that layer or do we not transfer that layer? We could also subdivide the layers into more granular pieces of transfer. So for our lifelong architecture search, we're basing it upon expectation maximization. What we have is two sets of parameters. The first set of parameters is shared between all the different tasks. We also have a set of task-specific parameters. And so when training up each task, the question is, for a particular layer, do I make it transfer-based or non-transfer-based? To perform the architecture search via EM, for each task, we already have a set of shared knowledge, and so we also initialize a set of task-specific layers as well. For the E step, we compute the likelihood of the model given the data, and then we let backprop flow through, adjusting the weights as to whether or not we should use a shared layer or a task-specific layer for each network. And you can see this by the thickness of the lines changing the diagram here. Then we go back to the E step, compute the likelihood of the model given the data, flow back through for the M step, and again, adapt the particular architecture configuration that we're using. And this repeats over and over and over until convergence. And eventually what we're going to end up with is a stable architecture for each task. And so, for example, in this case, you can see that task 1 has task-specific, the first layers is the first two, followed by a shared layer, followed by a task-specific layer, followed by another shared layer, whereas for task 2, it's two task-specific layers followed by the rest all shared. So what we found was that incorporating architecture search into the lifelong learning process improves performance. And what we see is that, first off, we just use a static transfer configuration. The range is really wide in terms of performance. If we try to transfer at all layers, you get the line that's in blue, which doesn't perform all that well. Instead, lifelong architecture search allows the automatic selection of an architecture which does much better than if we chose a transferring at all layers or a randomly chosen static transfer configuration. In comparison to using lifelong architecture search to optimize the transfer configuration versus a brute force search, what we can see is that they perform approximately the same. However, LASEM with the expectation maximization is about 5 times to 10 times faster overall. In terms of comparison to alternate methods, things like APDNet or progressive neural nets, we can see that LASEM performs very competitively, both in terms of a high accuracy and a low forgetting ratio. So the forgetting ratio is near 1, meaning it's retaining most of its knowledge, whereas things like APDNet, for example, do catastrophically forget. So far, we've seen ways of factorizing knowledge in a way that works for deep networks. Now we're going to go into more modular representation, specifically looking at how we can take lifelong learning and move it toward using compositional representations. And we're going to look at this for both classification as well as reinforcement learning. To present this work, I'm pleased to introduce my PhD student, Jorge Mendez, who's been focusing on this for his dissertation.
One of the main motivations, if not the main motivation, for work on lifelong learning is to discover reusable knowledge. Of course, this is very challenging because the agent has to find knowledge that it can reuse in the future without knowing what that future even looks like. This is in addition to the problem that we've been discussing so far of avoiding forgetting. Now, note that we not only want to avoid forgetting because we want to be able to solve previous tasks, which we certainly might, but also because we want the agent to solidify that knowledge so that it becomes more and more reusable. The hypothesis driving this part of our work is that functionally compositional knowledge representations, and we'll tell you exactly what we mean by that in just a few minutes, enable modular reuse across a lifelong sequence of diverse tasks. For now, just imagine that our functionally compositional knowledge structures are neural net modules, and we want to combine these modules into a different neural net for each task. So each puzzle piece here in the figure represents one of these modules. We created a framework for learning these kinds of modular solutions in a lifelong setting. And the key to the framework is to split the learning process into these 4 intuitive steps, which are inspired by Piagetian theory and are designed to encourage knowledge reuse. First, the agent initializes the modules on the first few tasks, for example via a small multitask training on these few tasks or by imposing a curriculum. Once these components have been initialized, the agent then tries to solve each new task only by combining the existing components, without modifying them. This forces the agent to really reuse that existing knowledge before moving to the next stage, where the agent incorporates any new knowledge discovered during training on the current task, either by adapting those existing components or by creating new components if necessary. This general framework can be trained with a range of base lifelong learning methods like EWC or experience replay, and it can also learn various forms of composition. To give an example, we're going to go back to the specific case of neural net module composition, based on the architecture of Meyerson and Mikulainen, which they use for multitask learning, and we adapt to the lifelong setting. We assume that each task T can be solved with a neural net FT. To construct each FT, the agent has access to a set of modules M, each of which is a nonlinear, fully connected, or convolutional layer, shared for all tasks. The goal is to reorder these modules so that each task gets a different new neural network. And to do this, the input is passed through the modules, and a task-specific selection vector, ST, softly chooses which module's output is passed to the next layer. And this process is repeated for every depth in the network, outputting the reconstructed FT. This example shows how our framework applies to one form of deep net composition, but in our iClear paper, we also show how it applies to other compositional structures, ranging from some of our earlier work on linear lifelong learning all the way to a more modern form of neural module composition. One remaining question is, how can we automatically grow the model to add new modules when the existing ones are just not sufficient? Our idea for doing this is to only add new modules if they significantly improve the performance of the agent on the new task. So what we want to do is compare the performance of the network without the new module and with the new module, and make the growing decision based on that. But doing that naively would require storing and training 2 separate models with their own set of modules. What we found is that this isn't necessary. Dropout is a technique that already enables training multiple neural nets in the same shared set of weights. We simply took this idea and applied it deterministically on the modules so that, say, half the times the agent completely ignores the new module and half the times it uses it. In the end, what we have are 2 working models, with and without this component, and we can compare them and choose to discard the new component if it's not needed. One of the major challenges of current lifelong learning methods is that they can't handle highly diverse tasks. Intuitively, a learner that can freely combine modules to construct different networks for each task should perform much better. To test this, we separated MNIST and Fashion MNIST into 10 binary classification tasks each, and CUB into 20 10-way classification tasks, and combined all these 40 tasks into a single large sequence of tasks for a single agent to learn them. What we found is that our method performs far better than naive baselines like training a non-modular model or training the same modular architecture jointly with standard lifelong methods. And in particular, only the variant of our work that uses replay and grows dynamically was able to successfully solve even the CUB tasks. We can also take a look at the dynamics of learning throughout the sequence of tasks. Each color here represents one task, and at the top we can see our compositional methods. These jumps at 100 epoch intervals show the adaptation of existing modules to the new task, And we can clearly see that there's no drop in the performance of the earlier task due to this adaptation. And additionally, we see that the modules improve over time. And so the first 99 epochs on each task, which just combine existing modules without adapting them, work better and better as more tasks are seen. Now we're going to shift focus to RL. In some of our previous work, we showed that factorized policy learning can achieve lifelong transfer on MetaWorld. Here we give the agent a sequence of RL tasks consecutively. We're not going to go into the details of how we train the system, but many of the ideas are variants of the general framework that we've been discussing up to now. What's interesting is that this robot leverages knowledge from having learned a bunch of tasks to more quickly learn to solve new tasks. Focus your attention, for example, down here on the left. While our system has already learned to dunk the basketball, the standard single task learner hasn't even learned to pick up the ball. Now we're going to describe how we adapt the compositional learning to this RL problem. We specifically focus on combining neural net modules for training RL policies. The intuition is that unlike the supervised setting, where we only have perception modules, in RL we have perception, control, and even combined modules that process perceptual inputs and use them to plan actions. Like before, we want to use a set of neural modules to construct a different neural net policy for each task. This idea is in some way reminiscent of typical hierarchical RL, with, for example, options. But these ideas are actually fundamentally different. The traditional hierarchical RL composes modules in time. For example, a robot cooking task might be split into steps like grab the ingredients, then combine the ingredients, then put the meal in the oven, and so on. In contrast, our notion of composition composes modules as functions, whose outputs are sequentially used as inputs for subsequent modules. And so at any given time step, multiple modules are active. This is more similar to the way robot programming pipelines are built from modules for perception, planning, motor control. Each of our neural modules intuitively represents one stage in this type of processing pipeline. To test these ideas, we created two sets of tasks that would benefit from such a modular pipeline, where several of the modules might be reused across multiple tasks. The first tasks are a compositional variant of minigrid. There are multiple tasks that each require reaching a target of a different color, interacting with some environmental object, and doing so with a different agent dynamics. Intuitively, a processing pipeline could have a module for each color target, a module for each environment object, and a module for each agent dynamics. And combining them into combinatorially many policies can solve all combinations of these tasks. We used this intuition to create a modular convolutional net that follows this exact pattern. The second set of tasks is a compositional version of RoboSuite that has a very similar structure. There are multiple objects to grasp, obstacles to avoid, and diverse robot arms. The goal is to find object grasping modules, obstacle avoidance modules, and robot driver modules. And so again, we build a modular network that follows this intuition. The algorithm we use for training these structures is quite interesting, but we actually want to focus on the end results that we obtained once we learned the modular architectures. If we give the agent the ground truth structure by telling it which target object, environment object, and agent correspond to the current task, then it can combine the existing modules not only to learn much faster, like we see on the left, but even to get zero-shot transfer by just combining existing modules, like we see on the center, and achieve backward transfer, like we see on the right. Improving performance of the earlier tasks by modifying shared modules with data from future tasks. Even if we don't give the agent the true structure and instead let it automatically find it, we still get faster learning, zero-shot performance, and no forgetting. None of the non-modular or monolithic methods can achieve all three, and even progress and compress fails to avoid forgetting. The results on the robotics tasks are a bit more nuanced. The modular structure wasn't quite able to achieve zero-shot transfer, but it did somewhat accelerate the learning of new tasks, as we see on the left. What's interesting is that once we try to incorporate the knowledge of a new task into the shared components, the green bar here on the right, its individual performance drops on average. But by updating modules with future tasks, this performance is partially recovered via backward transfer, the red bars. In this part of our work, we created a framework for automatically discovering pieces of knowledge in a lifelong learning setting that can later be recombined and reused to solve future tasks. This showed that lifelong learners benefit from splitting the learning process into stages that encourage knowledge reuse and using compositional structures that enable adapting the model structure for each individual task. One of the challenges that we have faced in studying functional composition, especially in RL, is that there are no benchmarks out there that allow us to learn compositionally and then extract insights from the compositional solutions. In our work, we are creating a benchmark for hundreds of different tasks, constructed compositionally from multiple robot arms, objects, obstacles, and goals. This is a complementary effort to MetaWorld or RoboSuite itself, which contain multiple diverse robot learning tasks. The idea is that these tasks can then be learned sequentially, and the agent could accumulate modules or skills and reuse them in solving future tasks. We'll be announcing the release on our Twitter account, so keep an eye out. We hope this will be useful for the community.
Thank you, Jorge. For the final portion of the talk, I'd like to discuss our ongoing efforts to take these algorithms for continual learning of perception and action and move them onto autonomous service robots. At Penn, we've developed a small fleet of autonomous service robots that are designed to serve as a test bed for lifelong learning algorithms. On the left, you can see our first generation robots. These robots were designed to be particularly low cost and so have some hardware limitations that limit the total amount of time we can deploy them. But they're designed to operate in the hallways of the university around people, performing tasks such as taking people on tours or escorting a person from one location to another, as shown in these two videos. On the right, you can see our second generation of our robots, which are far more sophisticated. They have a much more robust base, enabling us to deploy them for much longer periods of time, and they also include an arm allowing us to do manipulation. Our goal was to have the robots deployed for extremely long periods of time around the university, and to, over their lifetime, accumulate a diverse variety of knowledge and skills. To evaluate lifelong learning in this application, we've conceived of a way of framing it in terms of a scavenger hunt of different objectives. The idea is to have a diverse variety of tasks that the robot would have to accomplish over time. So this is a collaboration between a number of different universities, and I particularly want to call out some work that was done at UT Austin in Peter Stone's group on framing an API for the scavenger hunt and setting up a website to actually run it. And you can see the link there, which I encourage you to visit. This is a video of one of our second generation robots performing the scavenger hunt in an expanded area in the hallways of Penn. In this case, it's received tasks to take a picture of a chair and take a picture of a laptop. So it has to model the distribution of objects and where to look for them to retrieve them, images of those objects as quickly as possible. You can see it navigating the area, scanning it to see where those objects might be located, and then finally driving up to each of them and taking the pictures. Once it has these pictures, then it uploads them into UT Austin's Scavenger Hunt API and their website to be validated. And the goal here is to have robots at many different locations and universities all performing different variations on the scavenger hunt, uploading proofs of performance of these tasks, and then having them validated for comparison. To finish out the talk, I want to revisit the key open issues from earlier, specifically focusing on these last two of non-stationarity and moving beyond tasks. In our application, where we have a robot deployed for extended time periods in an environment, there's naturally going to be changes, both in terms of the environment as well as in terms of the objectives that the robot is going to be tasked with accomplishing. In this case, there's non-stationarity. And so forgetting needs to be assessed with relationship to the distribution of those tasks, both the current ones that the robot's going to be expected to accomplish, as well as potential future ones. As a starting point for this, we do have a paper that provides a framework for how we might think of outer distribution learning, including in the context of lifelong learning. The second issue is that we as a community largely think of the temporal stream as being segmented into a sequence of tasks. We could think of it in terms of a sequence of classes too if we're doing class incremental learning. But this is really unrealistic. In real life, we don't have a single task that we're doing. Instead, we have this mix of overlapping skills that we're performing at any point in time with multifaceted objectives. And so as a community, I would encourage us to move more towards this idea of task-agnostic learning, where we have both abrupt changes as well as more gradual changes within the task distribution and in terms of what we're learning. This may also change the way we're thinking about accumulating knowledge. Instead of learning knowledge on an individual task basis, instead we may want more reusable skills that can be dynamically composed together to handle different objectives over time and their natural variations. I want to thank you all very much for your attention and especially acknowledge all of my current and former students whose work contributed to the topics discussed in this. This work was a massive joint effort between a lot of the people that you see here on the slide. And I also want to very gratefully acknowledge the funding from different agencies over the years. This work would not be possible without all that support. Thank you very much for your attention, and please feel free to contact me if you have any questions.